Hello, I'm the leader of this project, which is a Pulper Machine. Before we begin with the video about the project, I would like to mention the people involved in it. First, we have the design team formed by Escobedo de la Torre, José Humberto, and Nevares, Mendoza, and Rosana. Then we have the manufacturing team formed by Martinez, Rodriguez, Juan Carlos, and Hernandez, Morga, Javier. And finally, the automation team formed by Reyes, Gomez, Oscar Alonso, and me, REYNA, GARCIA, Jennifer, SUSANA. There are some points that I would like to mention before we begin with all the design and manufacturing stuff, and the first one is to explain to you what is a pulper machine. Basically, a pulper machine is an instrument used to improve the production time of the pulping process. And what does the pulping process involve? In a few words, is to take off the shell and the seeds of the fruit to obtain the pulp, which is used to make products like juices, acts, and jams. This process begins when the fruit is peeled and then cut into smaller pieces if it's needed. Then the fruit is screened until we obtain a kind of paste or something. And finally, this paste is filtered to avoid seeds or pieces of shell in the pulp. Assuming we want to process between 1.5 to 3 kilograms, this manual process will take between 50 to 80 minutes and it will require 2 to 3 people. The third point I would like to mention is that there are different types of pulper machine. They are classified according to the production rate is needed. We have low, medium, and high production rate. An example of a low production rate could be a juice stand where people only process the fruit according to the number of customers they have. On the other hand, we have the high production rate. An example could be an enterprise like Jumex or Del Valle that produce large amount of products per day. Now we are focused on the medium production rate, which includes artisanal goods or small enterprises. Now, talking about the objectives and social focus of the project, the main objective was to design and build a machine that is efficient and that fulfills the task of separating the pulp from the other fruit components, to facilitating the task for the producers of caquetas, sates, and jams. And we also are looking for a machine that reduce the physical effort and optimize the production time and increase the production of the enterprise. And as I said, we are focused on the small businesses. We want them to grow. We want them to be able to accept big jobs, to able to compete between them, to compete with the big enterprises. And we also think about the job vacancies that our machine will create.
First, we looked for some designs on internet, and in some places we found this kind of designs, and we like them. But they are well too expensive, so we decided to simplify as much as possible the machine so it will be cheaper. And the construction basically is the entire body made out of stainless steel, because we don't want to contaminate the food as we are working directly with it. And the pulleys are made out of aluminum and the bearings of cast iron, so there's no risk of contamination. We are using a Siemens engine of 1 horsepower and a nominal velocity of 1760 RPMs. There's not much information on the internet about the hardness of the fruit, but we know that around 900 newtons we can crush it. And as we are working with already cooked fruit, we don't need that much force, so a small motor is enough. We are using a pulley drive because of the distance between the shaft and the engine. This kind of drive allows power to be transmitted between long points, distances, and they are easy replaces. The belt can be easily replaced, and they can reach high speeds. So for the selection of the pulley, we have this graph, and we have the horsepower of the motor and the RPMs. So looking at the design, we need a 3V belt, and as we want to reduce the speed, we need a much lower diameter for the driver which is of 1.41 inches, and the driving has to be 4 or 5 times higher. So we have a 7.75 inches diameter for the driving, and some calculations like the length of the belt of 1070 millimeters and the angles of contact in the pulleys, and they are not the best, but they are acceptable and they can move all the mechanism with no problem. The velocity radio, we are reducing speed and gaining force. The belt speed moving at 3.204 meters per second. And finally we have the belt length. This is a graph with some commercially available belt lengths on the market, and the most similar to the one we need is the 42.5 inches length. So with some tensors we can adapt it to the design.
Talk about our transmission, why we chose it, and some of its advantages. First of all, it consists of a belt drive with pulleys. Its main function or its main purpose is to transmit rotational motion from one shaft to another. We chose it because it is cheap, it produces less noise than other mechanisms even if it's working at high speed. It requires low maintenance, also does not need any lubrication, and it is easy to install. The belt, we chose it with a V shape because this causes the belt to wedge tightly into the pulley, and this increases the friction and hence the torque. And the torque is very important to us in this project. So now that we established our transmission, we can now calculate the torque generated by this one. In order to do that, we needed to know the value of the initial torque, which is the one given by the motor. And it has a value of 3.9576 newtons per meter. And the one that we calculated is the one transmitted by the driven pulley, and it has a value of 2165 newtons per meter. And as I stated before, the transmission that we chose increases the torque. And as you can see here, the final torque or the resultant torque is way bigger than the initial one. And now with these calculations, we were able to do the torsion analysis, and also we obtained the maximum shear stress and the safety factor of the material. So here in this part, you can see the torsion analysis, and in this specific part of the shaft or in case or axis, we added the 21.75 newtons per meter, which is the torque, and at the end we obtained a maximum shear stress of 7.17 megapascals. And as you can see here, compared to the numerical analysis, it is the same value. So here you can see our safety factor, and as you can see, the final value is 3. So this means that our shaft, or in this case our axis, can handle or can support 3 times the load that we are applying to it. So we have an example here. In case that we overpass that value, you can see that our shaft is completely in red color, and this means that it is starting to break or to deform. So now if we adjust it at 2, which is under the limit of the safety factor, you can see that the shaft turns into a blue color, which indicates that it is completely fine and nothing is happening to it because we didn't pass that value. So we choose a value of 2 just to be sure and to keep in good shape our machine.
Let's talk about the material. We decided to use stainless steel since the machine will be working with wood, therefore this material was the perfect choice. In a wide variety of stainless steels, we had 3 options: the 430, the 304 and the 316. The 304 is characterized by its resistance to corrosion, and it has way more compared to the 430. Regarding the price, the 304 is not as expensive as the 316, whereby the 304 was the picked one. The machine was welded by the MIG process with shielding gas, where a wire electrode was used. According to the American Welding Society, the ER309 LSI wire electrode is the suitable when welding 304 stainless steel. The shielding gases that were used are argon and carbon dioxide. The welding machine used was this one. As we can see, the machine has two knobs. The one at the top controls the wire speed in a range of 1.3 to 7.6 meters per minute. It is divided in 10 positions respectively. The other knob controls the output voltage and it is divided in 4 positions, A, B, C, and D. The wire electrode was observed and simultaneously the shielding gases, which were 0.030 inches and argon and carbon dioxide respectively. The gauge of the stainless steel used was 18, and as shown in the chart and having the other parameters, the configuration of the welding machine was this one. The letter B for the output voltage and 2.5 for the wire speed. This part was the one mechanized by the CNC milling machine, considering this is one of the parts that requires more accuracy. As shown in the video, the piece was first roughed down with a pocket operation, then a contour mill was made. After that, the piece was roughed down again twice, the same as the first one with a pocket operation, and in order to release the piece, a buzz was carried out at the end.
Here we have machine finished. The machining processes used to make this machine was turning for the shaft. In this place we turn and turning for pulleys. The other machining processes were drilling to fix the bearings. Here we fix with bolts and nuts, and to fix this other bearing. The rest of the machine were welded. Here we can see the blades. Now we're going to assemble the machine. The first step is to set the cylinder. Now it is set. The next step is to fix the shaft and blades. We can see how it rolls. And cover this extreme of the machine. We set this piece where we put the fruit this other cover where the seeds go out. Now we're going to check our machine. Here we have the cooked fruit. It's soft, you can push it with your hands. And we're going to get some pulp from this cooked fruit. The fruit gets into the machine by this hole, and after that the blades roll and push the fruit over this mesh. Here we obtain the pulp, and by this other extreme we obtain the seeds. Here our machine is running. This is the fruit, and we can see how the pulp appears around the cylinder. Doing this process by hand, it takes a lot of time. After a few minutes, all the cylinder is covered by pulp. You can see we don't have seeds here, only pulp. And here we can see only seeds. The machine works.
First of all, the type of controller. In this case, we decided to use the Mega 328P microcontroller, which can be easily found in the Arduino Uno development board. The reason we decided to use said microcontroller is because for our project we required at least 80 digital pins, and this microcontroller has at least 14 digital pins, so it has more than enough. It also has the I2C communication protocol, which we required to use to communicate with the LCD to show error messages or the timer for timer function that we decided to implement in our machine. It also has analog pins with 10 bits resolution, which is equal to 1024 steps, which is precise enough to choose correctly the time for timer function. It also has other advantages, such as the low power consumption, that it does not require an additional programmer or burner to program it. There is also low cost. It has a simplified and user-friendly programming language. It also has a larger library documentation. And in the most important aspect, it has an easy to manage package, a THT package, which means through-hole technology. This makes the diagram and PCB design much easier, and it's easier to work with this type of package as we can use it on breadboards. Now the security elements. In our machine we have at least 3 security elements. The first one that every machine has is the emergency stop button. This button cut off the power supply for the whole machine, including the electronics, so that it stops the machine no matter what when it's required to. Next we have the door sensor, that it tells us when the door is on or not, and the machine will not work if the door is open, so that we don't contaminate the product or expose the users to mechanical parts. It also has a fluid sensor that is not only used for the timer function that we implemented, but it also serves as it detects something for more than 2 seconds. It knows that something that shouldn't be there is obstructing the pace of the fluid, so it stops the machine if it's required. Now the electric connections. Here's the diagram for the electronic parts with a microcontroller and all the external components that it requires to work. It also has the relay with the transistor to turn on and off the AC motor. It also has all the inputs, the switches for the door, the timer function, the LEDs for show messages, and the AC to DC correction. Another reason for this microcontroller was that it works without volts as everything else on this diagram, so that we only require one power regulator for the whole electronic part. This is the PCB design that we came up with. Now for the Reyes connection. Here we can see the motor connection with the thermal relay, the relay to turn it on and off that is controlled by the microcontroller, and the emergency stop button, as well as the connection for the ground. Now for the wires connection, we decided to use a caliber of 16 that supports 13 amperes. This is more than enough for our project as it never consumes more than that. We also decided to use an ABB type of connector to have a more robust connection and is more secure. For the electronic parts, we decided to use an UTP cable that can be easily found as solder, and as the part doesn't need to move too much, this wire is perfect for said use.
Now I'm going to talk about the sensors and actuators of our system. In the category of sensors, we have 3 buttons. We have a limit switch for the door that will act like a security element. Then we have a potentiometer for a timer function that we decide to include to the machine. Then we have a fruit sensor that will be located on the bottom of the machine. That is also a security element, and a switch to turn on and off the timer function. Then in actuators we have the motor that is basically the most important component of the machine, and a LCD screen. And in other components we have the relays that are in charge of turning on and off the motor. Now more of our components are focused on this one. As you can see, we have 3 buttons, one to turn the machine on, one to turn it off, and the red big button is a emergency stop button. Then we have the LCD screen where the reminding time of the timer function will be shown, and also an error message if it's needed. Then we have the timer and the switch for the timer function, and we also decide to include relays to indicate the operator if the machine is on, if it is off, or if there's an error that he needs to check. Talking about the consumption, as you can see, the consumption of the electronics is not that much. The component that consumes the most is the motor, that consumes 746 watts per hour. So we make some calculations, and the total consumption of the machine per month of 22.5 kilowatts. What will be the automated process be? Well, the first part of the process, of course, is to introduce the fruit in this cone-shaped part, and this part is connected to the perfect cylinder, so the fruit will be like going in the cylinder. And then when the amount of fruit that we want to process is in the cylinder, the blades will begin to rotate and beginning to create this paste that I mentioned in the beginning. And after that, we'll be helped by the gravity or something, because the pulp will be going out through the holes of the cylinder, and the pulp is going down, so the shell and the seeds that are heavier will be going down, and they will go out. The trash, if we can say it that way, will be going out through the machine. This automated process will take between 20-30 minutes, assuming we want to process the same 1.52 kilograms that I mentioned of the manual process, and it will only require 1 to 2 people. Now, finally, talking about the budgets and costs of our project, we separate the budget in 2 categories, the manufacturing and the automation, and this gives us a total of 14,110 pesos, and we have a tentative selling price of 32,450 pesos. And that's pretty much it. Thank you for watching.